with all of you virtually, and my name is Velu. I'm a final year PhD student in cognitive and brain sciences. My advisors are Dr. Elisabetta Farella from the Digital Society Fondazione Bruno Kessler and Dr. Marco Boiati from the Center for Mind and Brain Sciences, University of Toronto. Today I'm going to introduce you to the world of EEG. In particular, I'm going to talk about bad channel detection problem and the solution that I proposed using local outlier factor algorithm. Okay, EEG electroencephalogram is basically the electrical activity measured at the scalp via electrodes. Here in the image, you see a person wearing a EEG cap with a set of electrodes that record the electrical potentials for each electrode, and then this data set can be used for further processing. The advantages of using EEG over other neuroimaging techniques are as follows. First of all, EEG offers a high temporal resolution in the order of milliseconds, so it can be really precise of the events that happen in the brain. Secondly, it's relatively cheaper compared to other imaging techniques, and it offers a wearable design. It's versatile. It's easier to make it a wearable device. And thanks to its easier setup, it can also be used to study newborns or very young infants, which is primarily my research area, over other neuroimaging techniques such as fMRI. EEG has this primary advantage. However, there are some limitations or challenges, I would say, with EEG. Since EEG records electrical potential in the order of microvolts, the contamination of biological and technical signals can really deteriorate the signal quality. To remove the artifacts, usually the researchers perform a set of pre-processing steps, which commonly involves filtering the usual settings for low pass at 40 Hz and high pass for at 1 Hz is used. Then the bad electrodes or bad channels are detected and removed from the data. Here I show a sample data set in which you have a set of bad electrodes. Then once the bad electrodes are removed, you go for bad segments removal, and here I show a sample newborn data set in which you see the portion of data that's highly contaminated with probably movement artifacts. Of course, in this talk, we are focusing on the second step, which is the bad channel removal. And what I would like to highlight is also the fact that depending on what you want to do with the EEG, the definition of artifacts changes. So for example, if you look for a specific frequency related information, probably you can tolerate some sort of artifacts. But if you look for a time domain analysis, the artifacts related to certain kinds will be intolerant. So we usually define which is the signal that we are interested in and the noise that we have to handle. Here I briefly explain what is a bad channel again. So with this sample epoch of EEG, we can see that clearly the electrodes or channels FP1 and AF7 are kind of anomalies compared to the neighbors. The channel FP1 in particular has just recorded the flat line, which doesn't have any neural information, of course. And channel AF7, in my opinion, is due to the fact that the electrodes are loosely in contact with the scalp, so it has recorded some sort of movements. Now let's look at the state-of-the-art measures that are used to detect bad channels. Kurtosis is one of the easiest and simplest measures that measure the higher order statistical fluctuations in the data. Then channel variance can also be a measure. Like I showed in the previous image, the variance for AF7 is relatively higher compared to the other channels. And Hurst exponent is a measure of the biological movements or motion. So it can really signify if the recorded EEG is from a biological source, which is the brain in this case, or not. Then the interchannel correlation, which measures the spatial correlation between the channels that are closest to each other. Then there is a measure called power spectrum amplitude, which is computed in the frequency domain after transforming the data using Fourier analysis or periodogram analysis. All these measures have been used in different pipelines that are widely cited in the EEG research. However, there are some limitations with these measures. First of all of these measures assume a normal distribution for EEG, which is not entirely true. Of course, it's true to some extent, but this sort of assumption can really deteriorate the detection rate. Then secondly, while after computing the measurements for using each of these measures, the detection threshold is derived using a standard deviation metric, which can be sensitive to the outliers present in the data already. And the third primary limitation is that all of these measures have been validated on only one kind of EEG. For example, the power spectrum amplitude was used in HAPE pipeline that was validated only on infants EEG, and there is no guarantee that this measurement could be valid also for data collected from adults or newborns. In fact, when I started my research with newborns data, I understood that all of these measures were suboptimal, leading to so many false positives. Then I understood that the key point is that all of these measures also miss out on the local hidden properties of EEG. Therefore, I looked for measures that can detect outliers in the local context rather than the global context. And one of the algorithms that I found to be optimal was a local outlier factor, which basically measures the local deviation of the density of a sample with respect to its neighbors, where the neighborhood is defined by the k nearest neighbor algorithm. To appreciate the LOF algorithm without getting into the details, let's have a look at this image, which has two clusters, C1 and C2, and clearly the points or objects O1 and O2 are outliers corresponding to the clusters C1 and C2 respectively. If we approach this problem, the outlier detection problem, in a global view, for sure O1 being far away from all of these clusters and the points can be detected as outliers, but the object O2 will be detected as good object rather than detected as bad, because the distance between C2 and O2 is not so far compared to the distance between C1 and O1. So if you adjust the threshold to also detect O2 as the outlier, then you risk to have so many false positives in the cluster C1. But instead, if we apply the local approach, since LOF is computing the density-based metric, it can effectively detect both O1 and O2 as outliers. Now let me briefly describe the algorithm here. The first step was to, for each object, in our case it's channel, k nearest neighbors are identified, and then the reachability distance between each of the neighbors is computed using this equation. Usually if the point O is closer to the point P, then we use k distance, whereas if it is far, then we use the actual distance between the 2 points. This is a kind of smoothing effect. The points that are closer to the point of interest can create some sort of statistical fluctuations, and using the k distance instead of using the actual distance can reduce these fluctuations. The local reachability density LRD is calculated, which is basically the average reachability, the inverse of the average reachability distance of P with respect to all of its neighbors. Finally, the local outlier factor is defined as the average of the ratio of local reachability density of the point P with respect to all of its neighbors. Now let us have a closer look at the LOF equation. So if I am the object P and I have a certain local reachability density, and all my neighbors also have a similar local reachability density, which will lead to an LOF of 1. And this also implies that I am within the cluster, so I'm not an outlier, right? So ideally, if I'm an inlier, my LOF score is 1. So you can say that if an object has an LOF score greater than 1, is already an outlier. However, this threshold is not really practical in real world applications, as also demonstrated by the original authors. Therefore, we employed a tenfold cross validation to identify the optimal LOF threshold. Uh, for the software, this this method is a part of newborns EEG artifacts pipeline. We publish this as an open source toolbox within the EEG lab software. And here you see the GUI, in which of course you have other methods apart from LOF. But recently I also extended this analysis to other subjects apart from the newborns, to adults or infants, to see the generalizability of this algorithm. And it was published recently in Sensors article, and we are going to see the results shortly. For the data sets, as I said before, I use newborns EEG, who are 0 to 4 days old. There were 21 newborns, and we used a high density EEG setup with 124 sensors, and we employed the frequency tagging design, which is really not important to define here, but just to say that it's acquired using a particular kind of EEG paradigm. And this comes from this study published by Buyati et al. In 2019. Then for the infants, we use another set of data sets, 9 months old, 28 subjects with the same kind of EEG setup. But here they use event-related design, and this was published in 2012 by Paris et al. Then finally, we also used adults EEG, which has 113 files, and this EEG was recorded using only 64 sensors compared to the other ones. And here the event-related design is used, and this is published in 2020. And in all of these data sets, the ground truth for the bad channels were visually inspected by the respective authors, and they are the experts in the field, so they clearly know how to deal with the bad channels. And thanks to their expertise, we have the ground truth for the calibration of LOF. Now let's have a look at the results. The first thing that I wanted to demonstrate is that LOF, compared to the traditional statistical measures using mean or median, is robust against the outliers present in the data. To do this, I took the measures from each channels, such as mean, interquartile range, median absolute deviation, and LOF computed with Euclidean distance and LOF computed with standard Euclidean distance. And I did an AUC analysis. Here we see from the scores that LOF, of course, is better than any of these standard measures, showing its robustness against the outliers. And this result is from the adult data set, but it's the same trend also for newborns and infants. Then as far as the detection performance concerned, I used a robust metric F1 score rather than using a classification accuracy, because the dataset is highly imbalanced. If I remember correctly, it's around 93% of good channels and 7% of bad channels in the data. And as we can see, compared to the traditional pipelines used in EEG research, LOF shows its robustness. Of course, it's not the best. There is still room for improvement, but so far among the automated methods, LOF shows its robustness. And the good thing is that it is adaptable to different kinds of EEG that has different number of sensors and acquired using different EEG paradigms. Finally, I also try to understand the range of optimal threshold in all of these three data sets. There is a clear trend here. Since the newborns data is very challenging, there is a lot of artifacts in newborns EEG because we cannot really control the population. They usually cry, they move here and there. That creates a lot of strange artifacts. And since the inherent signal to noise ratio is low, a relaxed threshold was found to be optimal around 2.5. Whereas if we go for adult EEG, uh, who are very calm when the EEG is being recorded in the lab, the LOF threshold is around 1.5, which is very conservative. However, there are some limitations, open challenges for LOF applied to EEG. The first thing that I observed is if I apply the algorithm on a limited channels, like a system that captures, let's say, 16 channels, LOF doesn't seem to be robust. Of course, this is an empirical analysis that I did just out of curiosity, and since it's a density-based algorithm, it makes sense that it's not suitable for low-density EEG setup. Then, for the fact that it's dependent on the threshold, it requires some sort of calibration, which means we need ground truth labels, which is very challenging in the EEG community because it's very hard to find open source data sets with labeled bad channels. Then finally, this algorithm is also quite computationally heavy, takes around 10 seconds to run each file in MATLAB. But since it's offline algorithm, I think it should be fine. So to summarize my talk, the presence of bad channels can affect the cognitive, experimental, and machine learning classification outcomes because the data acquired using these channels are not really related to the brain. The kind of artifacts differ according to the EEG settings, the population that we are studying, and the kind of application that we are working. The existing measures look at this problem as a global approach, and they are sensitive to outliers present in the data themselves. Therefore, I proposed local outlier factor for the first time applied to EEG, which doesn't assume any distribution for the data and captures hidden local properties in the signal, which is also robust against existing outliers. And the key thing that we found out in this research is that it is adaptable to any kind of EEG once the threshold is calibrated, which makes it a sort of a global measure for all kinds of EEG data. The code is available in GitHub, which is compatible with EEG Lab, and I'm also working on a Python version, which is hopefully to be released soon within a Python library used in EEG signal processing. Now I'd like to thank you for your attention, and I'm available for any curiosities or questions. Thank you.
Thank you for your interesting presentation, Velu. And now we can ask questions by raising your hands.
Yes.
Yeah, Angelia, please.
Yes, thank you for the presentation. I have a question about slide 6, where you show the plot with different points. I was wondering, how you convert your curve to this point, or what represent these points?
Okay, this is just to demonstrate the algorithm in general, but
Okay.
yeah, we can consider that these points represent the channels. So
Okay.
usually from the neuroscience perspective, the electrodes that are over here in the frontal region of the brain, they tend to have similar kind of amplitude compared to the ones collected from the occipital region of the brain. So we can imagine that the channels in the frontal lobe can be here as C1, and channels in the occipital lobe can be here in C2. And we have some outliers which have to be detected.
Okay. Okay, thank you.
No problem.
And Yamini, please. Hi, Yamini. We can't hear you. Hello.
Yamini, I think you are muted. Okay.
Hello, can you hear me now?
Yeah.
Yeah.
Yeah. Thanks a lot for the presentation. So my question is about the data sets that you selected. Why exactly did you aim at the newborns and the infants? You could have selected probably more adults what is the main purpose of choosing infants as the data set? Yeah.
Thank you for the question. Of course, my research is about newborns EEG, so I was looking for a measure that can primarily work in newborns. But since I found this algorithm to be very effective, I tried to expand it to different data sets. For adult EEG, of course, I can also do more analysis on adult EEG, but those existing measures that I presented before, they are more or less effective in adults EEG data, because these subjects are, we can control these subjects. We can ask them to be quiet, not to make any movements, so that we do not have so much of artifacts in the data. And these traditional methods can already work better. But with infants and newborns, it's a more challenging scenario. So that's another reason why I considered those data sets.
Okay. And another question would be about the algorithm that you selected. Why exactly did you choose the KNN, and why not other similar algorithms to measure the distance?
I experimented with a lot of algorithms in my initial years, and for the labels that I had, I found that this one was predicting the bad channels very much closer to what the researchers in cognitive science do.
Okay.
But I'm pretty sure that there can be other algorithms that can probably outperform this one. Yeah.
Okay. Yeah. Thank you. Thank you again for the presentation.
And is there anyone want to ask questions? The Anelia, please.
I see. I live 1 year before me. So.
Thank you, Angelia. Hi, Velu. Thank you for your presentation. So my question is, in this picture, how do you compute this distance between two channels, and what kind of features did you choose?
Okay, so there is no feature here. It's just the time series data as it is. For the distance, like I mentioned in the results, I tried with different distance metrics, and among them, standardized Euclidean was performing the best. It's very comparable, but in some data sets, standardized Euclidean distance was performing better. So in fact, these results are acquired using standardized Euclidean distance metric.
Okay, so one more question is about how did you get the ground truth? I guess I think I probably missed this part. Maybe you have mentioned, but how do you get this ground truth?
How do I get, sorry, what?
The ground truth.
The ground truth, it's from these authors. So they visually inspect the data. In fact, in a few years ago, the traditional way to detect artifacts is to visually inspect the data. Each file, they have to go through scroll through the data and then look for the bad channels. And the ground truth here is given to me by the respective authors of this study.
Okay, so I see. So they are all public data sets, so you just use them,
Yeah.
right? Okay,
Exactly.
thank you.
No problem. In fact, we are kind of forced to accept this as the ground truth. Otherwise, we don't have any other way.
Okay, thank you. And Amelia, do you want to ask questions? Oh, okay.
Okay, yeah, was a curiosity. Did you find some difference between newborn and adults in terms of number of bad channels that you detect? Or there are some difference? I expect maybe in infant you have more bad channel, I don't know, because they move.
Yeah, but apparently, I mean, to my surprise, in all of these data sets, the ratio between good and bad is kind of similar, around 93 and 7. Since we also calibrate the LOF threshold, so since we are using a very relaxed threshold for newborns, this balances out the number of bad channels. So here, of course, the number of bad channels would be, the detector would be higher because we are using a strict threshold for adults, right? And for newborns, if we keep the same kind of threshold as 1.5, we would be detecting more number of channels as bad because they are noisier. So yeah, the trade-off is balanced by calibrating the threshold.
Okay, thank you.
No problem.
And I find Yami is still raising your hands. And do you want to ask questions?
No, I think it's the old one.
Okay.
Yeah.
Okay. And then Ivan want to ask questions, please.
No, so can you hear me?
Yeah.
Okay, so it's about the infant. So basically, I believe you said that the noise came because they were crying or things of the kind, right?
Yeah.
Well, I'm thinking, so did you try when they're sleeping, or this would also affect the results, things of the kind? So if you get them when they're kind of sleeping or at peace, I'm thinking because the brain would still be performing, right, or things of the kind.
Oh, sorry, I think I lost you. Can you repeat?
No, I'm saying that collecting the data when the infants are sleeping, would that have an effect on the output? Or
When they're sleeping, even
yes.
these data sets are not collected while they are sleeping. They had to do some sort of cognitive experiments. In this case, they had to listen to their mothers speaking some words. So the data is not collected when they are sleeping. But if your question was about collecting the data when they are sleeping so that we can reduce the artifacts, yeah, but since we are interested in their cognitive perception, I think they have to be awake.
Okay, cool.
They
Thank you.
have to do usually some sort of experiment. So in the newborns, they had to see a face-like pattern that was shown in the computer screen, and we try to understand if they can differentiate between two different images, for example. So they have to actively do some sort of work.
Okay, thank you.
Okay, I think there is no questions. And thank you for your presentation. And bye.
Thank you very much. Goodbye.